Welcome back, guys, to your physical geography class. Today we're going to be going over chapter 3. It's going to be a shorter lecture than last week's. We're going to be looking at the atmosphere and what the atmosphere is composed of. We're also going to be looking at the different layers of the atmosphere. So let's get right into it. Size and composition of the atmosphere. If I were to ask you, what is the atmosphere consist of? Well, most of you would say air. Yes, the atmosphere is made up of air, right? But what exactly is air? That's what we're going to look at today. There are different types of gases that make up our atmosphere and that make this planet this livable place, right? This is one of the unique portions of our planet that makes it livable. If we think of the air above us, the air around us, we can think of it as this vast ocean of air, right? And it's held to the earth by gravity. Now, we cannot feel that heaviness of air, but it's there. And later on, when we talk about pressure, that same idea comes into play. Just like a lobster or a crab at the bottom of the ocean cannot feel the weight of the ocean, we don't really feel the weight of air, okay? So when we look at the concentration of the air or the mass of the atmosphere, where is more air at? At the very top, like very high above where planes fly, or at the very bottom? Where is there more air? So your answer should be closer to sea level, right? So if you were able to see our imaginary air around us, there would be more air molecules closer to sea level. These are air molecules. It's really hard to draw here, but these are little circles of air, right? Obviously invisible. And as you go up in the atmosphere, way up here, there's less of them, but there's more concentration closer to where we're at, closer to sea level. So if you were to take a box of this air versus a box of this air, which box of air has more air? Closer to sea level, right? So there's more mass closer to sea level of that air. Density is higher here than up here. So the mass is concentrated at lower altitudes. Now you can, I'm getting ahead of myself, but you can experience this, right? Because there is a pressure change. Because there's more air here, there's higher pressure at sea level than there is up here. There's lower pressure because there's less concentration up here than there is right here. Does that make sense? Like when you go to Big Bear, or when you go to the mountains, or when you get in an airplane, you can feel that difference in density, right? You can feel the change of pressure. There's less pressure at higher elevations, okay? So that will be more chapter 5, but I want you to understand how our atmosphere is distributed. There's more air closer to the surface of Earth, or closer to sea level, I should say, than there is at these higher altitudes. So we're going to look at our composition of our atmosphere. So we know that there are different gases in the air, right? So we're going to separate them in two different types of gases. First, there's permanent gases, and then on the second page, there's the second slide, there's variable gases. So permanent gases, take some time here. You're going to have to write these down. These are never changing, no matter where you go, what time of year it is, what day, how much humidity there is, what you're experiencing, is it hot or cold? These will always be fixed. So they have little to do with weather or climate. They don't influence our weather or climate. What are these permanent gases? Permanent gases are, give me 1 second. I don't know why this is harder to do. Nitrogen, oxygen, and you're probably doing a better job of writing this down, and argon, A-R-G-O-N. Okay, so write those down. Oxygen, nitrogen, and argon. These are permanent gases. No matter what, these will never change. Nitrogen will always be in the atmosphere at 78%. This is important, very important slide. This is important to write down your notes, guys. Nitrogen will always be in the atmosphere, and it will always be, always, no matter where you're at, what time of day, blah, 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 it will always be 78%. Oxygen will always be 21%. And hopefully you're listening and not just watching. And argon will be about 1%. About, give or take. Okay? So no matter where you go, you will always have 78% nitrogen in the atmosphere, 21% oxygen in the atmosphere, and about 1% argon. They're the two most abundant gases in the atmosphere are nitrogen and oxygen. Okay? So permanent gases, they never change. So our composition of the atmosphere is made up out of gases. The types of gases are permanent gases. We're done with that now. Now we're moving on to variable gases. So if permanent is non-changing, what do you think variable means? Yes, correct. Variable gases change from place to place. They vary from place to place, day to day, time of the year. So these change. Like it could be there's more of these in Australia or in the tropics versus in the deserts, okay? So I'm just throwing things out there. These will have a great effect on weather and climate. These will have a huge effect on what we are experiencing in terms of weather, okay? So have any of you ever been to Florida or Alabama or Louisiana or the West Coast? I'm sorry, the East Coast, southern East Coast states. If you have, what do you notice about the air there? You should say humid, right? So yeah, it is super humid there. And that's because there is more water vapor in the atmosphere. So water vapor is one of the first examples of a variable gas. Water vapor obviously is water in the form of gas, and water evaporates. We can't see it, but it is a gas, and it's called water vapor. Water vapor does have an effect on our weather and our climate, right? The more water vapor there is in the atmosphere, the less evaporation happens, the more condensation begins to happen, and then we have more rain begin to fall, okay? It is invisible. The visible form of water in the atmosphere is clouds and rain. Water vapor is the most abundant overlying warm water surfaces. So within the tropics, which is closer to the center of the earth, right? Tropic of Capricorn, Tropic of Cancer. I mean center, by what I mean is the equator. Sorry about that. You have warmer waters than in the Arctic Circle or the Antarctic Circle, right? So right here, right at the equator, is where more of the sun hits it all year long, right? So all that water there is constantly being warmed. And what happens when you warm water? It evaporates, right? Now in Earth's systems, water that evaporates becomes a cloud. Does that make sense? Or it just becomes very humid type of conditions. So if you visited any place close to the equator, it's more humid all year long. So if you've ever been to, I mean, you can even sense it when you go to Cancun, Mexico, right? Anywhere close to the tropics, closer to 23.5, 30, even 30 degrees north or south is still considered tropics. You're going to feel that humidity, okay? So first type of variable gas, you have variable gases that do impact weather and climate. First type is water vapor. Second type is carbon dioxide, okay? Carbon dioxide, or CO2, has significant influence on climate, huge, okay? Because it is able to absorb radiation and helps warm the lower portion of the atmosphere. So how do we get carbon dioxide in the atmosphere? So many different ways. It is naturally produced, but you can also say that it's produced by human origin, right? car combustions, transportation industry. Anytime you burn a fossil fuel, it releases CO2 into the atmosphere. And, you know, even if humans were not here and we didn't invent all this stuff, or we didn't use fossil fuels and we didn't burn them, carbon dioxide is naturally found in the atmosphere, okay? It's there, but you cannot deny the fact that along with the natural causes, humans are adding more carbon dioxide, CO2 in the atmosphere, okay? So what is happening now, and I'm kind of going off, well, not really, it's still on topic, is because there's so much CO2 in the atmosphere, we're getting something called ocean acidification in our oceans. So if you look at the Earth is more water than it is land. 70% of it is water in terms of surface, right? So you look at all the Earth, the surface of Earth, most of it is water and it hits the atmosphere. So the atmosphere is heavily concentrated with CO2. And the oceans act like this natural filter. They naturally take out CO2 from the atmosphere. So as they do that, because there's too much CO2, it is changing the chemistry of the ocean. Because of all the burning of fossil fuels, all the extra CO2 in the atmosphere, the ocean is working overtime, okay? So it's changing the chemistry of the ocean and it's now becoming more acidic. So what is happening? We call this ocean acidification. And what are the effects of this? Unfortunately, there's huge effects on ocean life. So for example, our coral reefs. Our coral reefs are disappearing. We've lost over 50% of our coral reefs in the past 30 years, and that's 5 years ago, so I don't know how far we've gone now. The ocean waters are getting too warm. They are too acidic, meaning that things with exoskeletons like, or even shells like clams, oysters, coral reefs, they cannot function and they cannot grow and acclimate to how quickly or how acidic our oceans are getting, right? So we know that water has this scale. It could either be very acidic or it could be alkaline. And I know that it's very popular right now. You buy alkaline water and it's so healthy, but whatever, right? So we know that there is like this scale for water. Our ocean water is now getting to that acidic side of the scale, and it's really affecting our ocean life. There will be a video for you to watch and a little, there'll be a link for ocean acidification. We will definitely talk about this more in the class, okay? So again, going back, what are we talking about? We're talking about the composition of the atmosphere. We talked about permanent gases. That's done. Permanent gases do not affect our weather and climate, nitrogen, oxygen, and argon. Now we moved on to these variable gases. Do they affect weather and climate? Yes, they do. First one was water vapor. Humid areas, you could feel that water vapor. Second one is carbon dioxide. Lots of carbon dioxide in the atmosphere, and it's been like, there's a lot more than there used to be, right? Another variable gas is ozone. So where do you think it's concentrated at in our atmosphere? What layer? The ozone layer. Yes, you guys are correct. In the ozone layer is where we find more ozone molecules concentrated. Yes, it's spread out all over the atmosphere, but it's concentrated naturally in this little layer that we call the ozone layer. Why is it important? Well, the ozone layer, invisible, it protects us from harmful UV radiation. So the ozone layer acts as like this natural sunscreen. It's very important. Methane. Methane is another variable gas that affects weather and climate, okay? And haven't got to how these gases affect our weather and climate, but I'm gonna get there, and it's a very, very important process, okay? Methane. Methane is a it is a variable gas. How is it produced? Many different ways. So methane is written like this, CH4, right? Why do I have this picture of gas? I mean, of cows. because cows do produce methane. Pretty much any living thing that eats food and digests food produces methane. I mean, even small bacteria in oceans and lakes is going to release methane into the atmosphere. Also, man-made things release methane. Anything that is being broken down releases methane into the atmosphere. Now, there is a lot of methane in the atmosphere, and the reason I have the picture of cows here is because if you're saying, oh, cow farts, cow burps, you're right. So too many cows, right? And all of them together, it really adds more methane into the atmosphere. It's not a joke. It really does. We're not talking about millions of cows. We're talking about billions of cows in United States alone, because think of how much we are eating beef and how much milk products we are consuming. Okay, so they're not, also the problem is that they're not eating grass like they were made or supposed to do, right? They're eating things like corn, which is a little heavier on their digestive system, so they're producing more methane. Okay, so one cow can produce I want to say a gallon of methane a day. So the video link that I'm going to have for you will show exactly how dangerous methane is. So if you take a molecule of methane, it's 32 times more potent than a molecule of CO2. So all these variable gases are also known as variable gases are, I forgot the word. They're also known as greenhouse gases, sorry. It's so much harder when you're not in the classroom. So all these variable gases are also known as greenhouse gases. They rise up into the atmosphere, they get they hang out in the atmosphere, and when the sunlight comes in, it warms the earth, warms the grass, warms the water, and instead of bouncing back out into outer space, because of the methane, water vapor, CO2, all that in the atmosphere, it's trapped inside, and then it produces warming. What do we call this? It starts with a pH. No, it doesn't. What the heck is wrong with me today? It's the greenhouse effect. I'm so sorry, guys. It's a weird day today. It's also a lot different to be in front of a camera than in the classroom. So it is the greenhouse effect. So variable gases are also known as greenhouse gases, okay? You're going to have a video on the greenhouse effect because it's a very important process. I want you to understand that variable gases are also known as greenhouse gases, okay? And I also want you to know that the greenhouse effect is not negative. If it wasn't for the greenhouse effect, we would freeze and we would die, or we would probably not be here, right? But the greenhouse effect is very, very important. Now, more of these greenhouse gases or more of these variable gases is kind of making that greenhouse effect work very well, right? So we're warming the lower portion of the atmosphere very, very well. What is that leading to? It's leading to a rise in sea levels. It's leading to ocean surfaces being warmer. It's leading to glaciers melting. It's leading to loss of plankton in the northern part of the ocean, the higher latitudes of the ocean. Is leading to loss of biodiversity in our oceans. So it's really having a huge effect on our planet, which we can call climate change, okay? Particulates, this is another portion of the atmosphere that is not gases, right? It's not gaseous. These are aerosols. They're kind of like these little things in the atmosphere that hang out there, but they're not gases. They're very small particles. We call them particulates, okay? They're non-gas particles in the atmosphere. They could be solid or liquid particles in the atmosphere. Examples of these are dust, volcanic ash, wind-blown soil, pollen, meteor debris, smoke from wildfires, salt spray from ocean, automotive emissions. So take a moment here and pause this slide. Back here it's supposed to say automotive emissions, and go ahead and write this down because you will be seeing this on your exam. What are some examples of particulates? Okay, let's move on. Particulates do affect weather and climate in two major ways. I just swallowed a little bug. You guys, that for reals, I just swallowed a bug because there's like little gnats. I can't erase this either. All right. Particulates affect our weather. That's going to be like a blooper. Particulates affect our weather in two ways. They reflect energy from the sun, or they reflect the sunlight, or they absorb sunlight. So they can absorb or reflect sunlight. So hygroscopic or reflection. So hygroscopic would mean that they absorb sunlight. So all those little particulates are in the atmosphere here. They're hanging out. When the sunlight comes through, hits the earth and re-radiates back out, it traps that sunlight, okay? Or they reflect sunlight. So past like really large volcanic eruptions have the power of dimming the earth. So all that soot, all that ash that is ejected because of that volcanic eruption, it hangs out in the atmosphere. When the sun comes in, that is reflected away. So we call that a global cooling or global dimming. We do have evidence of that happening a long time ago. That hasn't happened in a long time. Or must have been like a super volcano is large enough to eject that type of volcanic ash into the atmosphere. So particulates, they're non-gas particles, right? They're particles in the atmosphere. Ash, salt, pollen, dirt, soot, automotive emissions, all these do affect our climate, okay? Just like gases keep our temperatures warm, they can also do that or reflect sunlight, okay? Vertical structure of the atmosphere. So the atmosphere is structured in different layers. Closer to the surface of the earth, you have the troposphere, then the stratosphere, mesosphere, thermosphere, exosphere. You are required to know these. So write it down, take some time to write your notes down. Troposphere is closer to the surface of the earth. It extends about 11 miles up, and planes still fly within the troposphere, okay? So most of our weather and climate, most of our weather happens within the troposphere. So our structure of our atmosphere extends really, really far. I mean, think of how high planes are. They don't even extend, they don't even go into the second layer of the atmosphere, okay? Troposphere is the first layer, closer to the surface of the earth. Air is always moving, okay? Air is always moving around. That's why most of our weather happens in that atmosphere, in that layer. Once you get to the stratosphere, air is stagnant. It's not moving around, so you're not going to have much action there, okay? Then you have the mesosphere, thermosphere, and exosphere extends into planetary space. Where is the ozone layer? Ozone layer is going to be found, I have it on the next slide. Here it is. The ozone layer is found above the troposphere, but not so within the stratosphere, you could say. Yeah, you could say that. Yeah, that's where the ozone layer would be here. Okay, so I'm going to go through this quickly. Temperature patterns in the atmosphere. Air temperature changes in the atmosphere are not constant. So as you move up within the troposphere, it does get colder, but that changes as you move up in the stratosphere and then the mesosphere and the thermosphere. You can't see this very well. It's okay, I'm just going to go through this, but it's not constant, okay? So air temperature changes are not constant within the portions or the structure of the atmosphere. Human-induced atmospheric change. Human activity has had major effects on the atmosphere, and yes, we are powerful enough to alter global climate. People will argue and say that man is not powerful enough to change the climate, but We are. You cannot deny the fact that the amount of CO2, the CO2 levels in the atmosphere have increased since the Industrial Revolution, and that increase is because of the burning of fossil fuels, okay? So it's not a small amount of data. There is a large amount of data that proves that. Altering global climate can harm forms of life. Yeah, climate does change naturally. We're not saying that it doesn't, but we also cannot ignore the fact that our climate is also being changed because our over addiction and overuse of fossil fuels. That is no way you can ignore that fact. Okay, how is it harming forms of life? We are living through the sixth mass extinction. We are losing more species in our lifetime. We are losing species because they are not able to acclimate to these environmental changes. Depletion of the ozone layer. Ozone layer, why is it important? Because it keeps us safe from that harmful UV radiation, right? So our ozone layer is thinning, but we have taken the right steps, some steps in the right direction since the late 80s to protect our ozone layer. So before there was a use and kind of like this dependence on these chlorofluorocarbons, CFCs, other substances that are altering and depleting the ozone layer are halons, methyl bromide, nitrous oxide. CFCs have been banned and they are slowly being phased out. There was the Montreal Protocol in 1988, part of the United Nations, that it was like a treaty that a lot of nations signed and said, okay, we're not going to use CFCs because it is damaging our ozone layer. So there is areas of the ozone layer that have thinned, like closer to the South Pole. You have a permanent kind of like this gap in the ozone layer. And you know, even if we phased out CFCs, they're still in the atmosphere. It's not like they just disappeared. It's only been about 35, 40 years that they were phased out. That's not very long. I know you guys are young spring chickens and 30 years sounds super old, but once you get to 30, you'll realize that 30 is not very long. All right. Causes of CFCs: industrial gaseous waste, cooling liquid, freon, foam and plastic manufacturing, aerosol sprays. So CFCs are not the only culprit to the depletion of our ozone layer. You have halons, methyl bromide, nitrous oxide, yes, those. But CFCs were used so widely in the past because they were non-reactive, they were odorless, they were non-corrosive. So that's why CFCs were used so widely in the past. What would happen if we didn't have an ozone layer? We would have higher amounts of UV radiation. What are some impacts of that? Obviously, it's harmful to human health, more autoimmune diseases, more skin cancers, cataracts, damage to plankton. Plankton is the building block of our water ecosystems, of our ocean ecosystems, not just the oceans, but lakes, rivers, and streams. They all rely on plankton. It's the base of that food chain, of that food web, right? So this leads to loss of biodiversity in our oceans, rivers, and lakes. That's scary stuff, right? The Montreal Protocol, 1987, that was the treaty that I was talking about. Something else that we have developed is the UV index. It was established to provide the public with information about UV radiation. So if you go to EPA.gov and you go to the UV index website, I think it's related, it might be on a different website. You can enter, you can do it for today, any day of the year, enter your zip code and it'll tell you, okay, UV radiation in your area is at an all-time high. Please apply sunblock every 2 hours, wear a hat, wear this. So they let you know how bad the UV index is. And that is because the ozone layer has been depleted and it thins out. It's not like a hole that happens, but those ozone molecules start to disappear. So there's less of them. It's like just a thinning of the ozone layer. That's what's happening. Air pollution, we're still looking at how humans have affected what our atmosphere, right? Atmospheric, human-induced changes to the atmosphere. Air pollution, humans alter the composition of the atmosphere, but I want you to understand that the atmosphere has always had pollutants, okay? Those have been always natural. It leads to reduced visibility, but pollution has been more widespread since the 1700s. Types of pollutants, there are primary and secondary pollutants. Primary pollutants, secondary pollutants, you guys don't need to know this. You guys can look through this. Consequences of air pollution. The last two slides is what I did want to get to. Weather and climate. We will be looking at these the entire semester. This is a physical geography class, but what's the difference, right? What I want you to remember is that weather and climate are not the same, okay? Climate is what you expect. Weather is what you get. So what does that mean? So say you are planning your wedding for October 2022 to make sure the pandemic is out of the picture. October 2nd. What type of weather are you expecting? What type of climate are you expecting? Yeah, nice conditions, right? Really, really nice. Fall conditions, right? That's the type of climate you expect. But you get to October 2nd and it's raining. So climate is long period of time data. It's really what you predict and what you've seen globally for a long period of time. Weather is going to be different for like La Habra, Cerritos, Buena Park. All these places have different weather, but you're expecting the same type of climate, right? So if you want a definition, weather is going to be short-term atmospheric conditions that happen for a given area for a given time, right? And climate is going to be the aggregate day-to-day weather conditions over a long period of time. You're looking at least 3 decades. Now, that's when 30 years sounds like a long time. 3 decades, right? I'm 3 decades years old. That's crazy. So let's call it 30 years. So weather is your day-to-day atmospheric phenomenon, right? What you're feeling here in Cerritos, California. And climate is the aggregate conditions over a very long period of time. You're looking at over 30 years. Not that long. Elements of weather and climate. Atmosphere can be complex, and everything that's going on within the atmosphere can be complicated or confusing. Its nature is usually talked about in terms of just some measurable variables. So temperature, moisture content, pressure, wind, right? All of these are basic parts of weather and climate. When we see how they differ from time to time and place to place, we can understand weather and climate better. Obviously, when we look at our phones, like, how hot is it going to be? Oh, 90 degrees is hot, right? Yeah, we're looking for the temperature. If we were to live in a different place, we'd probably look at the humidity, the moisture content too, right? Pressure has a lot to do with our weather. And you'll learn about that on chapter 5. Why pressure, a ridge of high pressure in the Great Basin. It means it's going to be hot here. Even if it's not even close, it does affect our weather, okay? Controls of weather and climate. So yes, we're looking at those other things, but these are also going to affect weather and climate. Latitude, right? How high up you are or low you are within latitude, right? The closer you are to the North Pole is going to be much different than if you're at the equator. So latitude is going to impact your climate, your weather. Distribution of land and water. If you live in San Diego versus Dallas, Texas, which one's closer to the water? San Diego, right? So they're going to have a much more mild winter, and we'll talk about that why specifically in chapter 4. They're going to have a mild winter versus a landlocked area in the interior of a continent. It's going to be a colder winter and a hotter summer. Circulation of the atmosphere, how the atmosphere moves, where you're located, how those jet streams move, and the winds and what they carry. General circulation of the oceans. Altitude, if you're high up in altitude, your weather and climate is going to be much different than if you're closer to sea level, right? Topographic barriers, if you live within a valley or on one side of a mountain, it's much different. That'll affect weather and climate. And storms, right? So these are very important. We are done for today. That was really quickly. And again, there's some things that I'm not going to hit on just because it's like you can read it yourself and it probably won't show up on the exam. So yeah, today was a very short and sweet lecture, but a lot of important stuff. And go ahead and finish up your module. And it was great to see you guys. Have a great rest of your day and have a good day. Bye.